let's look at polar graphs, which we refer to as roses. So the general equation for a rose is r equals a sine of n theta, or r equals a cosine of n theta. And so what we need to look at is, what does the a do to the graph? How does it affect the shape of the graph? How does the n affect the shape of the graph? And then how does the sine and the cosine affect the shape of the graph? So just to kind of see where the graph comes from, again, let's look at comparing the polar graph, r, and in this case, we'll use the specific graph, r equals 3 sine of 2 theta. So that's our polar graph that we want to look at. And we want to compare that to its rectangular version, y equals 3 sine of 2x. So again, the x value on our sinusoidal graph is going to correspond to the rotation, the theta, the angle in our polar graph. The y value on our sinusoidal graph is going to correspond to the radius, the radial distance r of our polar graph. And again, remember the sine graph. Normally, y equals sine x has a period from 0 to 2 pi. But in this case, we have a 2x. We have a 2 theta. And so if you remember when we talked about our sinusoidal graphs, putting a number in front of x changes the period of the graph. And so if we put a 2 there, if you take 2 pi and divide it by that 2, so 2 pi over 2 is a pi. So that means our sinusoidal graph actually only has a period of pi. And if we do that graph from 0 to pi, and we actually extend it to go from 0 to 2 pi, that means we're going to see 2 periods between 0 and 2 pi. So looking at our sinusoidal graph, again, we're going to see 2 periods of this graph. It starts at the origin at 0, 0. It's going to go up to its maximum, down to its minimum, and back to the middle of the graph at pi. And it's going to repeat that. It's going to go, starting at pi, it's going to go up to the maximum, down to the minimum, and back to the middle of the graph at 2 pi. So it's going to do that twice. But doing that twice is only going to correspond to one full revolution around the unit circle. Okay, and so we want to see what this looks like. Remember that when the 3 in our equation, y equals 3 sine of 2x, that 3 corresponds to the amplitude of the graph. And so the amplitude in this case, the sine wave goes from the x-axis up 3 units to 3 and down 3 units to a negative 3. Okay, so that means our radius values are going to go from 0 all the way extending outwards to a 3, and then also extending to a negative 3. And remember, what does it mean in polar coordinates for a radius to be negative? It means that it flips it diagonally across the origin. Okay, and so we saw this when we looked at our limacon graph too. Anywhere that our sinusoidal graph is below the x-axis means that the corresponding part of the polar graph is actually going to flip in the opposite direction of our angle. Okay, so keep that in mind as we look through this. All right, so let's just kind of track through. We're going to start, our starting value is at 0, 0. So that means a 0 angle and a 0 radius. So it's a point at the origin. Our rotation is at 0 degrees or 0 radians, and so that is the positive x-axis. As I take my sinusoidal graph and I move to the right, I will hit the maximum value of 3 at pi over 4. So as I rotate from 0 to a pi over 4 angle, I'm going to start at 0, and my radius is going to increase to 3. And it's going to hit that 3 at pi over 4. Okay? So I've seen the rotation go from 0 to pi over 4. My radius goes from 0 to 3. As I go from pi over 4 to pi over 2, that rotation going from the 45-degree angle up to the y-axis, I'm going to see the radius track from a 3 back to a 0, which means it's going to go back to the origin. So it's going to reach the origin when my angle hits pi over 2, so the 90 degrees. And so it creates kind of this loop. Okay, and we're going to see multiple of these loops, which we're going to call these loops petals, and that's why we call it a rose, right? Because a rose is made up of petals. So as we continue to rotate, as I rotate from pi over 2 to 3 pi over 4, and then eventually to pi, as I rotate through the second quadrant, notice on the sinusoidal graph that that loop, that portion of the graph is below the x-axis, which means as my angle is rotating through the second quadrant, the actual coordinates are going to flip diagonally into the fourth quadrant. So notice as my angle is pointing into the second quadrant, as I continue this rotation, my angle is in the second quadrant. Once it hits 3 pi over 4 in the second quadrant, right, then I'm at a negative 3y value, which means I'm at a negative 3r value. So instead of that point being in the second quadrant on the 45-degree angle line, it's actually in the fourth quadrant at 7 pi over 4. And then as we continue rotating towards the x-axis, we'll see the radius go back to 0. So we've actually created two petals, one in the first quadrant because we rotated through the first quadrant, and one in the fourth quadrant because we rotated through the second quadrant with a negative radius. As we continue rotating through the third quadrant, we now have positive values for our radius. And so we're going to create a third petal in the third quadrant. And then we're going to rotate out to the 3 and then back to the origin once we get to 3 pi over 2. All right. As we continue rotating through the fourth quadrant, again, notice the y values are negative, which means the radius is negative. As we rotate through the fourth quadrant, we're going to see a petal in the opposite direction in the second quadrant. And it's going to reach the tip of the petal at the it's technically the petal is at the 3 pi over 4 angle, but it's corresponding to the 7 pi over 4 angle, right? Because it's negative radius flipping across the origin. And so we'll continue rotating until we hit back to the x-axis at 2 pi, which is going to bring us back to the origin. So the y equals 3 sine of 2x equation is a wave with amplitude of 3, so it goes up to 3 and down to negative 3. It's centered along the y-axis, and its period is 0 to pi. So we see it have a double period. It repeats its period twice between 0 and 2 pi. The graph of r equals 3 sine of 2 theta in polar, it is actually a rose with 4 petals. And if you look at each of those petals, they each have a radius of 3. So hopefully you're kind of seeing some of the nature of what the rose looks like. So let's go ahead and shift and look at a few more examples of roses just to see how that 3 and that 2, if we change that 3 and 2, how does that change the shape of the graph? And if we change it from a sine to a cosine, what happens there? So what we've seen already is we know that r equals 3 sine of 2 theta is a rose with 4 petals. Each of those petals connects at the origin. Each of the petals is oriented along the 45-degree angles in each quadrant. And each petal has a radius of 3. So each petal extends outwards to the sort of concentric circle of radius 3. So let's see what would happen if we change that a value. Okay, so as a gets bigger, what happens to the petals? So say we wanted to look at the equation r equals 7 sine of 2 theta. We still have 4 petals. They all connect at the origin. They're all at 45-degree angles in each quadrant. Well, the only thing that's changed is the size. They all have a radius of 7. All 4 petals extend outwards to the concentric circle of radius 7. Okay, so hopefully we can kind of see that whatever that a value is, it will represent the radius of the petals. Okay, so that's the easy part. So what about the n? So right now n is 2, and we have 4 petals. So let's go through some different values for n and see what we get. So if n is 2, we have 4 petals. If n is 3, we actually only have 3 petals. If n is 4, it turns out we have 8 petals. If n is 5, we have 5 petals. If n is 6, we have 12 petals. What do you think will happen if we have n is equal to 7? We've seen if n is 3, we have 3 petals. If it's 5, we have 5 petals. So it might make sense that if n becomes a 7, we'll have 7 petals. And that's actually what happens. So r equals 5 sine of 7 theta. We have 7 petals. They all have a radius of 5, and they are all evenly spaced apart from each other. So if you took the whole revolution around the unit circle from 0 to 2 pi, and you divide that by 7, so 2 pi over 7, that's how far each of the petals are from each other. Okay, so that's the amount of rotation you could think of from the tip of each petal to the next one. It would be 2 pi divided by n, so 2 pi over 7. Okay. So if n is odd, then n is actually equal to the number of petals. Well, what about if n is even? Okay, so if n was 2, we had 4. If it's 4, we have 8. If it's 6, we have 12. So what kind of relationship are we seeing? If n is even, you're going to double that. So if n was 8, how many petals are we going to have? If n is 8, we're going to have 16. Okay. And this is the sine function. Notice for the sine function, where are all of these 16 petals? So for r equals 5 sine of 8 theta, again, there are 16 petals. They all have radius 5. They're all evenly spaced, so 2 pi divided by 16 now. Right, that's how far apart they all are. Notice that all 16 of these petals are within the quadrant spaces. So we have 4 petals in quadrant 1, 4 petals in 2, 4 petals in quadrant 3, and then 4 petals in quadrant 4. So they're all within the quadrants. None of them, the only place they touch the x or the y axis is at the origin. Okay, so if n is even and you have a sine graph, all of the petals are contained within the quadrant spaces. Okay, and that's going to be true as long as it's even. So if n is 6, we have 12 petals, which means we have 3 inside each quadrant. If it's 4, we have 8 petals, 2 inside each quadrant. And if it's 2, we have 4 petals, 1 in each side each quadrant. And they're all, again, evenly spaced. Okay. What about if it's odd? So if n is 3, we have 3 petals. One of those petals is on the y-axis. In fact, it's on the negative y-axis. Okay, so if n is 3, we have a petal on the negative y-axis. What about if it's 5? We still have 5 petals now, but one is on the y-axis. Nothing on the negative y-axis or the x-axis. So only on the y-axis, positive y-axis. If n is 7, we have 1 petal on the negative y-axis. So where do you think the petal would be if we had n equals 9? It's going to be on the positive y-axis. My graph doesn't go that high, but if we did, we would take the n equals 7 graph, basically flip it upside down, so 1 petal is on the positive y-axis. We just have 9 petals just evenly spaced around. Okay. All right, so I think hopefully that describes what the rose looks like. If you had 1 petal, right, it goes up. So what we see it is the number of petals if you have an odd number of petals, and it's a sine graph. You're always going to have 1 petal on the y-axis, and it alternates between the positive y-axis and the negative y-axis. So if n is 1, it's up on the y-axis, 3 is down, 5 is up, 7 is down, 9 is up, and so forth. Okay, so hopefully that summarizes, describes what we see for the roses with even and odd petals. So let's see what happens if we have cosine. So right now, if we have r equals 5 sine of 2 theta, there's 4 petals, radius 5, and they are all contained within the quadrant spaces. If I switch that to cosine, so r equals 5 cosine of 2 theta, we still have 4 petals, they still have a radius 5, but now they're not contained within the quadrant spaces, they're actually contained on the x and y axes. So we have 4 of them, 1 on each of the axes. Okay. So what happens if we go from n equals 2 to n equals 4? We do, again, get 8 petals. 4 of them are on the 4 axes. The other 4 are spaced inside the quadrants. If n is 6, we now have 12 petals. 4 of those are on the axes, which means the other 8 have to be divided up evenly between the 4 quadrants, right? If n is 8, we have 16 petals, which means 4 of those 16 are on the axes. The remaining 12 have to be evenly divided between the 4 quadrants. Okay, and again, all of them are evenly spaced as you go around the circle. What if n is odd? So r equals 5 cosine of theta, that's actually just one petal. It's technically a circle on the positive x-axis. If n is 3, we now have 3 petals. One petal is on the positive y-axis. The other petals are just evenly spaced around. N equals 5 petals. One petal, again, is on the positive x-axis. The other 5 are just evenly spaced around. The other 4 are evenly spaced around. If n is equal to 7 petals. One, again, is on the positive x-axis. The other 6, they're just all evenly spaced around. Okay, so with cosine is more consistent. Cosine, you always, if it's odd, you always have a petal on the positive x-axis. If it's a sine, remember it alternates between the positive y-axis and the negative y-axis. All right, well, let's summarize what we've seen about these rose graphs, and then we'll try to look at some examples. Okay, so the equations of roses have the form r equals a sine of n theta, or r equals a cosine of n theta. And the roses are just graphs that contain multiple petals, right? The radius of each petal is given by the a value, so the coefficient in front of the sine or the cosine. The petals are always evenly spaced around the circle. Okay, so if you know if you want to figure out how far apart they are spaced, take 2 pi and divide it by how many petals there are, and that will tell you how far apart they are. Okay, if the n value is odd, then that n value tells us how many petals there are. So if n is odd, that's how many petals there are. If we have a cosine of n theta, then we will always have one petal on the positive x-axis. If it's the sine equation, then that one petal will alternate on the y-axis, either the positive or the negative y-axis. Remember, 1 is up, 3 is down, 5 is up, 7 is down, and so forth. Okay. If n is even, then the rows will have double that amount. So the rows will have 2 times n petals. If it's cosine, we will always have, however many petals there are, 4 of them will always be on the x and the y axes. Okay, one on each side, and top and bottom. Okay, so we'll have 4 of the even number of petals will be on the x and y axes, and the rest of them are just evenly spaced. If you have the sine graph, none of them are on the axes. They are all within the quadrant spaces, and they're just, again, evenly spaced around. If you take the number of petals and divide it by 4, that tells you how many you have in each quadrant. Okay, so let's look at a few examples here. We'll start with a couple where we're given the graph, and then we want to find the equation, and then we'll look at a couple where we flip that around. So this first graph, we have a rose with 3 petals. So since that's an odd number, right off the bat, I already know that n has to be 3, okay, because it's an odd number of petals, and so n has to be that number. We also see that one petal is on the x-axis. So because it's on the x-axis, that tells me this has to be a cosine graph. And I can tell that the radius of that petal is 7. Okay, and so if the radius is 7, that tells me the value of a. So I know a has to be 7. I know it has to be a cosine graph or cosine equation, and I know n is 3. And so that's everything I need. Again, the graph is r equals a cosine of n theta. So we're going to have r is equal to 7 cosine of 3 theta. Okay. All right, let's try another one. This time, if we count up our petals, we are going to have 12 petals. So 12 petals. Since that's an even number, we need to take half of that. And so that means n is going to be 6. So if n is 6, that means you have 12 petals. And if you look at all 12 of these petals, which are evenly spaced around, notice that none of them touch the x or the y axis except at the origin. Okay, so that means you have 3 in each quadrant for a total of 12. Because none of them touch the axes, they're all in the quadrant spaces, I know that this has to be a sine graph. Okay, so I know the number of petals. I know it has to be a sine graph. So the last thing I need to figure out is what's the radius of each petal. So it looks like the petals are all extending outwards to the circle of radius 7. So I know A has to be 7. Okay, so that means my equation is going to be R is equal to 7 times the sine of 6 theta. All right. Okay, let's look at a couple equations that we can then try to sketch the graph. So this first one, we have r equals 4 sine of 5 theta. The 4, the a value tells me the radius. So I'm going to go ahead and I'm just going to take my graph here. Now I'm going to draw a dotted circle along the circle of radius 4. Okay, if you don't have the grid, just draw that dotted circle and say it has a radius 4. Because of the 5 theta, 5 is odd, so I'm going to have 5 petals, all right? And they're all evenly spaced. And because it's sine, I know one of those petals is going to be on the y-axis. Now I have to figure out which. Okay, for sine, remember it alternates. So 1 is up, 3 is down, 5 is up. So this is going to be on the positive y-axis. And again, it has a radius of 4. So let me draw one of my first petal. It's not necessarily the first petal as we draw if you were to generate the graph rotating around the circle, but just in terms of drawing it freely here. I'm going to draw my first petal on the y-axis going up, and that's going to be the first one that I draw. Okay. From there, I need to draw 4 more, and I need to try to draw them so that they're all evenly spaced. So take the whole circle and divide it into sort of 5 parts. So you might have another one sort of lower in the first quadrant and another one lower in the second quadrant. And then you're going to have 2, one down into the third, and then another one into the fourth. So I don't know the exact angles. We could easily compute those. Again, it's just 2 pi divided by 5. I'm not super picky on how that you get them all perfectly spaced, so at the right angles, but just, again, roughly speaking, I have 5 petals. 1 is going up on the y-axis, and the other 4, all 5 together, should be evenly spaced. Okay. All right, last example here. We have r equals 6 cosine of 4 theta. So again, the 6 tells me that's my radius. So I'm going to go to the circle of radius 6, and just so I can kind of see where that's at, I'm going to just kind of do a dotted circle there. And I know 4 theta tells me, since 4 is even, there are going to be 8 petals. Okay, so 8 petals. They all have a radius of 6. And because it's cosine, I'm going to hit all 4 axes. Okay, so 1 petal extends from the origin in the positive x direction out to that circle of radius 6. Another extends along the negative x-axis. Another one extends in the positive y-axis, and then again on the negative y-axis. So I have 8 petals, and I've just drawn 4 of them on each of the 4 axes. So I have 4 more to draw. And they have to be evenly spaced amongst all of them. And so that means the other 4 petals should be inside the quadrants. Okay. That was not a very good loop there. But so that's sort of what our graph should look like. Again, it doesn't have to be perfection. This is just a sketch, so just be a rough drawing. But ideally, again, we'd like to see a radius of 6 for each petal, 4 of them on the axes, and then the others are evenly spaced.